Alrighty then. Good morning to everybody here. Thanks for having us. My name is Maik from Keysight Technologies, accompanied today by my colleague Lukas. Thanks for the nice introduction. And in advance, I'd like to make an apology because we just flew in from Germany. So any mind fog related to jet lag, apologies in advance, all right? Okay. What this presentation will cover, we don't want to have a product pitch. We don't want to have project results demonstration. We just want to give you some initial thoughts that we have as a test and measurement company on how you can have measurable trust in an AI validation environment. So we thought about this long and hard, and actually we just wanted to give you some of our initial approaches on this, start the discussion with you as you are all experts, because nobody right now can just give the complete answer to that, so we need your help on it. Get on to us, challenge us afterwards, we are here. Let's start on what this is all about. So when I'm presenting in Germany or in Europe, I usually ask, being a test and measurement company in the heart, in the very core, what do you know Keysight? So please, a bit of interaction here. Who of the audience here knows Keysight? So please, hands up. 1, 2, 3, 4, 5, 6, 7. All right, thank you. Being a test and measurement, of course, I like to compare the results to the German results, and it looks better. Also, who does not know Keysight? Hands up. Okay, thanks. So a lot of undecided ones as well, so far so good. So this is basically an analogy to the approach we were taking because I got some results from you, giving you a task, your human neural engine a task of providing some results for that question. And I got some yeses, got some no's, some undecided ones. The interesting question is, some of you answered yes, and thank you for it. The question is, why did you answer yes? So maybe some of you said yes, of course I know Keysight, I've got some great instruments, I know them, perfect. Maybe there was a yes because maybe I should know Keysight, so I just raised my hand, just in case. Or maybe a third option, just out of politeness for the presenters, let's just raise a hand, okay? And this is the core question which we're looking into later as well. We get some results out of the machine learning process, but how valid are they? How trustworthy are they? So please keep this kind of first initial task in mind. So as there are some no's and undecided ones, I quickly will start about introducing Keysight, just a little bit, not too many marketing slides there. And then we will go over to the main topic on T&M's role, so test and measurement role in AI. What can we do? Where do we see us today and in the future? And the next very important thing is something to do with cheese. Here it is. No worry, this is a plastic one, so no smelly thing here. So far, so good. Then we have a walkthrough on a very interesting use case, which Lukas will take over, which kind of gets a bit of more insight in what we actually want to do there. And then, of course, it's the call to action, challenge us later on at the booth, wherever you like. So, Keysight. There is this story of some guys in a kind of a shed founding a company in the Bay Area. Usually this story is kind of owned by the company with a kind of fruity image, you know. But it's also true for Hewlett-Packard because Hewlett-Packard back in 1939 founded their first company on electronic test and measurement equipment. And this is basically the origin of Keysight Technologies. Because as you can see here, it started with Hewlett-Packard, then in 1999 became Agilent Technologies as a spin-off of Hewlett-Packard, Agilent taking over all the electronic measurement stuff. And then there was a second split in 2014 when Keysight kind of was spin off again, Agilent remaining the kind of more medical stuff like biotechnical instruments, that kind of stuff, and Keysight taking over basically the core testing and electronic measurement solutions from all the way back to the Hewlett-Packard years. So as you can see, quite a legacy we have there. So what industries are we serving? It's not only automotive. Automotive is rather a small part right now, but we are here and trying to improve this, okay? So commercial communications, aerospace, defense, then automotive and energy, semiconductors, and also general electronics. These are the main industries which Keysight serves with their solution. renowned for, let's say, oscilloscope, spectrum analyzer, signal source, that kind of stuff, but also bundling together products with intelligent software to kind of create new solutions for the evolving markets in the future, for the digitalization, which is currently ongoing and will carry on. Just to give you a few numbers on the background, so market position as test measurement company right now, Keysight owns place number 1. So we turn over kind of $5 billion a year with 40,000 customers, and we are very proud of having a huge R&D, people like Lukas here. So we have 22 R&D sites all over, spending a lot of money and effort there to always bring the new technology first to the market. We have more than 100 countries which we directly serve, and I don't have checked the stock value as of today, but it's around that kind of 25 billion. Being a global company, of course, and having global customers like tier 1s, OEMs, not only from automotive, Keysight needs to be global as well. So what you can see here is basically where we spread it all over the world. So being close to the customer, having especially some automotive centers you will see in Hachioji, in Shanghai, also in Berlin as well, in Novi in the US, where of course also Santa Clara is basically, and Santa Rosa, the customer's main center. Just to give you a quick introduction, I don't want to spend too much time on it. So let's get back, let's focus on the challenge and the approach we had when I asked the question to begin with. So TM's role in the age of an AI. So usually, as you know, we are specialized in testing and validating the physical world. And when it comes to AI, what's Keysight currently doing is, of course, we have solutions like the Keysight AI data center builder, the sampling oscilloscopes, and the performance tester. So everything, of course, you can test and measure on the physical layer, latency, throughput, data optimization. This is something which we do already on a daily basis. But the important question is, how can we as a T&M company support the AI model as such when we, let's say, go to the semantic level and not only stay within the physical level? And this is the questions we came up with to begin with. So, of course, as you have noted from the other presentations as well, AI is data-driven. Data is the core of nearly everything. So, of course, we as T&M also collect a lot of data. And then the following questions are the most important ones. So maybe AI testing needs completely new paradigms. So which KPIs to use? Are there any out there? Are they accurate? Are there new ones needed? Who defines these KPIs? And how to manage then the test for AI as such? And when the testing has been done, also a very critical question. In the end, in between, or even all the time? And to make things even more complicated, as if this was not enough, you also need to stay within conformance of different standard and AI acts which are out there. I know it's a kind of a dull topic, but I just want to briefly discuss this. To stay conformance to like ISO 8800 and the acts on AI on a global scale, you need to fulfill these different tasks here. So you need a thorough documenting, you need proper testing, how to test. You need a proper validation, how to validate, and then, of course, some continuous improving to stay compliant with these, because you will have the situation where somebody asks, well, your AI and the results of it, do you actually have conformance to, let's say, the ISO 8800? And you need to document this that you have. And this is a very crucial part of it. And how do you come to that point where you say, well, I'm confident in what I'm delivering, what my AI is doing, I've done enough validation and documentation, but who can you ask if you're maybe a bit uncertain or you need new inputs for what you've done already? So my call to action today is ask your trusted T&M expert on AI, which as of today is Lukas Klose. So Lukas, the stage is yours, and he will explain you more thoroughly what this all has to do with that kind of block of cheese here.
Yeah, well, thank you, Mike. Thank you for the kind introduction. Thank you all for being here. Before we dive into this AI validation, I want to talk a little bit more about this cheese. And we are not insane, not completely at least. We want to talk about the Swiss cheese model of accident causation. I'm sure quite a few of you guys are aware of this analogy, but let me go ahead and quickly summarize it anyway here. In a safety-critical safety-critical system, there are multiple layers of defense. And those defenses can be, for example, out-of-bounds checks or checks for missing values. Now, no piece of software, no piece of equipment is perfect. There are always some issues, some holes in this layer of cheese, if you will. some bugs which can cause this layer to fail. However, normally this is not a problem because there are several layers stacked behind each other, and the possibility that a hole is going through the complete block of cheese is quite slim. So we really have to be aware of those cases where all holes line up, and we really have a hole going directly through the cheese. So let's come back to the AI topic and apply this to AI validation and see how this analogy can help us to tackle the challenges Mike just told us about. Well, when talking about AI these days, we most likely talking about some kind of deep learning model, and to be more precise, some kind of neural network, some kind of ANN, CNN, transformer layout, you name it. All of those neural networks have one thing in common. Based on their structure, the sheer number of parameters and neurons in the system, they are virtually black boxes. And of course, we all know black boxes are tremendously difficult to test. So, especially, now my presentation notes us. Oh, okay, thanks. Sorry. So, when talking about those challenges, right, we have to see how those models are faring, if there are some holes. And for all we know, our AI model as a block of cheese, right, can have some holes, can be completely hollow, and we really have to make sure that we can test this. So, using standard metrics, like for example, calculating the accuracy precision for classification tasks, or something easy like a mean square error for a regression task, can reveal some of those superficial holes and craters in the cheese, but we cannot really be certain how the inside looks, right? For all we know, it might be completely hollow inside. So we really make sure that we are not just testing superficial, but we really have to dig into the cheese. And the question is, how can we find those holes in the inside? And of course, this is not a trivial endeavor after all, right? The cause for errors can be obscured. There can be some false assumptions, some missed biases, spurious correlations, you name it, right? And another difficulty layer on top of this is that the root cause can be propagated over different layers, different stages of our development process. Meaning an error made in the beginning can become obvious only later in stages in testing, or even worse in the inferencing. So we really have to find a way to cut open the cheese to really see each step of the lifecycle model of an AI on itself, make sure that we discover those holes in the middle, right, plugging them, and thus creating, during the development process already, a safe approach. So, of course, software development for automotive systems and safety critical systems in general is well, very different to the AI development lifecycle. So the question is, how can we make sure that those two processes align? How can we align an AI lifecycle test model to the classical V model for safety critical engineering? Well, and of course, we have a 5-step program for this, or 5-step idea. And well, of course, first of all, we start with the data and problem analysis, making sure that we understand the problem we want to solve and know what data we need to solve those issues. Then, of course, we have to take a look at our features. What can we do with those features? Do we have enough features? Do we do some augmentation? How do we split our data into different subsets for testing, training, and validation? And only then we can really go to the model training the model, making sure it's fitting to our problem, it's finding the right solutions before we can go ahead and evaluate our model, making sure it's ready to be deployed in the domain. And finally, we can go to the inferencing stage, deploying our model, and making sure that it's still always good in the real world, or if we have some changes. We heard about retraining and finding the right spot about retraining earlier today, and this is exactly those challenges that had to be monitored in this part of the process. So, with this out of the way, I want to continue with a very easy and striking use case to walk through the AI lifecycle with you together. And how could it be different than talking about traffic sign and traffic sign classification? Please keep in mind, this is a little bit simplified to make those challenges more obvious, right? Okay, in ADAS task, in ADS task, identifying the correct traffic sign is crucial. We need to know who has the right of way, how much is the speed limit, and so on. And of course, it's mandatory to correctly identify the traffic signs in every situation. And well, in a regular day-to-day basis, this might be quite trivial, but there might be also cases where we have some unexpected situations. Some decals, for example, stuck on signs, rotated signs, deteriorated signs with age. And sometimes we even have some adversarial problems and very unexpected events, right, where the complete meaning of signs is altered. So, to give one example out of the streets of Germany, we have a lot of construction sites. Oh boy, basically all streets are construction sites all the time. And every construction site has a construction site sign. And me personally, I think I never seen a sign which is posted in a standardized way there. They are either too high, too low, rotated, bent out of shape, or completely beaten up. And I'm, as a human, I'm perfectly capable of understanding those signs nonetheless, right? And we all know that the idea behind AI is that AI can work with those signs as well. And I completely agree. I would assume this too. The problem is that assuming is not enough, especially for safety-critical processes, right? Maik told us about ISO 8800. We really need to have a way to document and qualify this belief, this assumption that our AI model is capable of dealing with those events. So this is all about testing and validating, and as always, we begin with the data. Collecting the right kind of data is not a trivial task, of course. Yeah, we need high-quality data. High-quality data really depends on the use case, so it's not about shiny new science all the time and high-resolution data. It's about data which fits our operational design domain. So the statistical distribution of use cases, of scenarios we're expecting in the real world. This might be, as I said, science with decals on it, science bent out of shape, etc. So we really need those signs matching the ODD. And now we are in a bit of a pinch. As an AI engineer, I maybe want to have like a balanced distribution, yeah, to give every sign a good possibility to be learned good by the model. And as a domain expert, I know that the ODD is very crucial. So we have to have this discussion about this trade-off. More balanced data, more data fitting to the ODD. And while there's no general solution to this problem, of course we need to document our findings and our decisions based on the specific use case. And therefore, both groups need to really understand each other. And therefore, we need a common language. And this common language can be a KPI-based or a graph-based language to really make sure that both sides understand each other and can work hand in hand to create this safe data set and high-quality data set. As soon as we have this high-quality data set, we can continue to the feature engineering stage. And here, I said it earlier, one important thing is, for example, data augmentation. So making sure that we're having enough samples in different, well, kind of iterations for the data set, meaning, for example, that we need rotated signs. Imagine we are having a 100 km/h sign, like the one on the left, and there's some lens flare on it. And we select this one for augmentation and rotating. Now we are creating the effects of the lens flare as well, rotating them too. This will create maybe a spurious correlation in our data set because now the model can learn a shortcut. Hey, weirdly orientated lens flare, this is a 100 km/h sign. And this is very dangerous. So we really make sure in every, after every step of our augmentations that our data set is still free of bias, free of spurious correlations. And well, the other challenge here is really about splitting the data set. Splitting the data set in test train validation is not a trivial task. Imagine you're sending out your fleet to record traffic signs. Now you're sending out your fleet, the fleet is waiting in front of a red traffic sign, for example, a traffic light, for example. And at least in Germany, there are some signs posted at those traffic lights as well. This might be, for example, a stop sign. Now you're standing there for 30 seconds, recording with 30 FPS, and as a result, you got 900 images of this stop sign. While the complete scene you see in your camera changes, the stop sign is virtually the same over those 30 seconds. It won't age a bit in this time, right? So if you now split the data set without care, you end up with basically the same sign in different subsets in train, validation, and test. And now you basically have a contradiction to the number one idea behind AI: don't test on your training data, don't train on your test data. So fixing this later on in the process is very expensive, right? You have to go back, retrain the model, redo your model evaluation, etc. And if you test at the right point, namely in the feature engineering stage, that something like this does not happen, well, this is way easier than doing it later on. After we made sure that this is well, done correctly, we can start the training. And all of you know that training an AI model is not just throwing in the model architecture or model description, adding the data set, maybe defining the learning rate, the initial learning rate, and some epochs and batch sizes, and well, start training and hope for the best, right? There are a lot of parameters to be set based on, well, high quality information. And also then we need to make sure that the model is actually converging, that it's actually learning our data set and our problems there. And one big issue is overfitting and underfitting, of course. And to tell a little bit about my time in school, when I learned vocabularies for English and Latin, I quite often learned the order of the vocabularies in the data set, in my vocabulary set I needed to learn, faster than the actual meaning. So I could tell you which vocabulary was in place number 2 or 3, but I didn't know the meaning. So I learned shortcuts. And this can happen to your AI model as well. And this will become a problem later on in deployment or testing, of course. So we need to make sure that the model is converging correctly. So then we can continue to the evaluation stage. And we decided to split the evaluation stage from the model training because we want to eliminate as many failed models in the training stage as possible to save on costs on the evaluation. Doing an AI evaluation for AI assurance is a very costly and time-intensive task, and therefore we really want to take only those models which are the best and have the highest chance. And of course, here's the question to answer: is the model actually ready to be deployed in our real life, in our domain we are targeted? So to make this sure, we need to find out if there are some unknowns, some unknown unknowns maybe even, some blind spots, and we need to take the system into consideration as well. So this is really not just about our AI model, this is also about our system, because we might know that there are some blind spots, we have identified them, and we can do something in our system, maybe a 2 out of 3 system or something like that, to prevent those blind spots from becoming a problem later on. And of course, another crucial key here is documentation. Documenting your results by combining different metrics, different results, and creating this comprehensive documentation, not just to know where to fix and improve your model later on, but also, in case of accident, to have something comprehensive to hand over to the DA, for example, and prove that there was no negligence. Okay, finally, we have a trained model, and we can go to the inferencing. And of course, this poses new challenges. There's the chance of domain shift or data drift based on, well, for example, like a few years back, the introduction of new kinds of participants, like the e-scooters, right? Does your model, has your model the capabilities to really understand those new challenges? We need to detect those failures before they occur, and then have the point of retraining. And this, well, progressive failure is really difficult to spot, because you don't want to retrain just arbitrarily, right? This is expensive. But we need to retrain as soon as we find some flaws and have this feedback loop, maybe like a SOTIF, like continuous improvement process, to really get to the core of those problems and find the optimal points. So normally this would be my last slide, but then yesterday we walked into this room and found something very funny right on this door here on the right.
Maybe we can have the spot on the door so everybody could see it in light. Can we change the light?
No.
No, okay.
But you can take a look afterwards. Well, it's an exit, but it's not an exit. So imagine you're an AI model. How do you decide? Well, I don't know. I, as a human again, can maybe guess that this is an exit, but maybe there's another room, another conference we don't want to disturb, and in the case of fire, we can use this exit door, but I don't know. But really, this is something where AI assurance gets into play to really understand how your model decides. Oh, and I think we can zoom a little bit on this. Yeah, so now there's actually another exit sign on the right as well. So let me quickly summarize now here. Explainability and understandability of your model is really not just nice to have. It's crucial to really connect the different stages of your AI lifecycle model and make sure that the model is well in every stage and find errors and fix them before they really occur. Remember, the AI model is like a block of Swiss cheese, and without cutting it open in different slices, it's very, very difficult to understand the inner workings and make sure that everything is safe. We at Keysight, as a test and measurement company, are here to support your journey as a company to deliver the best product, the best AI model for your use case, for your customers in a safe and quick manner. And therefore, we invite you, as Mike said in the beginning, really, to challenge us with your AI problems here today at booth number 3 outside. Come to us, talk about your problems with us, and we are very looking forward to your challenges. And with this, I think we are done. Thank you. We are open for questions.